2 to the x over natural log of 2. Is that starting to get in your brain? Anti-differentiating exponentials. Yes? Okay. This is a optional. I don't know if you could do that mentally, so be it. But what's the antiderivative of that second term? 2 square root x plus 1. Is that about what you have? Okay. Sounds good. Second one requires both knowledge of exponential derivatives and chain rule. So y prime is, what's the derivative of that first term, please? Times natural log of 5. That completes the derivative on the exponential, but then chain rule 2x, right? That's a lot. Okay. The other one's just gross quotient rule, or did you bring it up in chain rule or product rule? Quotient rule? Okay, do you agree we could do 2x times x plus 1 to the negative 1/2? We could do product rule if we wanted to. All right, so low root x plus 1 d high 2 minus, not plus, minus high 2x. What's the derivative of the square root of x plus 1? 1 over 2 square roots of x plus 1, all over the square of the denominator, so x plus 1. We? Yeah. All right. Today's lesson is a good one and important for you physicsy kind of people, except my slides are in a weird order, so let's fix that. Okay, so I'm on those set 74. I know it's weird, but you already had set 74 from Friday. We just didn't do the lesson, right? Okay. So now you're getting the notes for set 74. Now we're doing your lesson on set 74. There are no notes for set 75 because it's continuity, and you've already done continuity. Cool. All right. Here's the deal. If we have time, maybe tomorrow we'll watch a little bit of a submarine movie. Have you ever seen the movie U-571? Oh, it's a great movie. Okay. Maybe we'll watch it tomorrow. Get some popcorn. Okay. So anyway, in the past I did that, but then I didn't actually have time to actually teach what I was supposed to teach, so that went bad. Now I need to do that a little after the fact. But imagine, if you would, a submarine diving down to a depth of 500 meters. The submarine is now feeling far more pressure from the water at that depth per square inch than it did at the surface, yes? Okay, has anybody scuba dived? Anybody ever scuba? I've never scuba dived. Has anybody? Nobody's ever scuba dived? Did you say yes? Did you, how deep did you scuba dive? 5 feet? Oh, you might as well just not scuba dive at all. 100 feet, okay. Did it feel different, just out of curiosity? All right. Isn't there something, though, if you come up too fast, you get the bends?
Yeah, well, if you have too much oxygen, your lungs will expand.
Oh, gotcha. Okay. Now, continuing then. Imagine, instead of a huge submarine, a little baby submarine was at the same depth. Which one feels more pressure? The little baby submarine? Or which one feels more total force? The little baby submarine or the big old submarine? The little baby seems like it would because it's so little, but in terms of how much total force on the object, which one has more total force on the object? What's the big one? Because it's bigger. It's got more area on which to feel force, yeah? And then imagine a submarine, instead of diving in water, it dives in butterscotch pudding, okay? Which one, the one in the water or the one in the pudding, feels more force? The pudding, okay? So the question then is, what are the variables affecting how much force an object feels by fluid when it's submerged in fluid? Or it also could be fluids within the object. It's the same principle. The main variables affecting force on an object submerged in liquid are, well, in the first case, when it dived down to 500 meters, it felt more force. And so what's the first variable at play? The depth. Okay? The depth. The greater the depth, the greater the pressure. The greater the pressure, the greater the force. Okay? The next, huge submarine versus small submarine. Surface area. Okay? And then the last, pudding versus what? The third variable at work is? Density of the fluid itself, the weight density of the fluid. All right. And that's, in all cases, in all three cases, they're all direct relationship, which is to say, as the depth gets greater, the force gets greater. When the surface area is bigger, the force is greater. They're direct, not inverse relationships. All right, now, take a look at an algebra E kind of problem that doesn't require calculus. Say it had a cube with edges of 1/2 meter submerged in a 10-meter deep tank. So you have, go with water. That's your water. The top of the edge of the cube is 1 meter below the surface. So you have a cube where the top edge is exactly 1 meter below the surface. Okay. Find the force on the top face of the cube. In other words, the total force exerted on this square face. What's the sum of all that force? Well, let's go with, first thing we're going to need is actually, excuse me, the relationship. As we talked about here, the force depends on three things. The weight density of the fluid. Now that is rho, not P, but rho. It's the weight density of the fluid. D stands for the depth, and A stands for the area feeling the force. We said there were three things at work here: the weight density of the fluid, the depth, and the area. And they're all directly related. There's not even a constant variation in it. All right, now I will give you the weight density of water, but you will soon memorize it. The weight density of water is 9,800 newtons per cubic meter. If I throw that in there, and I don't usually carry around units, I'm a math guy, not a science guy, but for the sake of this problem, I think I will. The depth. What's the depth that this guy is feeling fluid at? That top face, is that a depth of? Is it 1 meter, 10 meters, what? 1 meter, just 1 meter. Okay. And the area. The area is the total number of, now that together is the pressure. Altogether though, how much area do we have feeling that force? 0.5 times 0.5 or 0.25 square meters. Total force then, what's a fourth of 9,800? You could do that mentally, half and half again, come on. And then say it out loud. I'm sorry, I forgot to say it. Are you raising your hand to answer that question?
Well, no.
Okay, hit it.
You have like different, we have a different thing on our.
You're just telling me this now?
Well, we're kind of just gonna go with the flow. I figured something else was happening. I was like, that's where it's going along.
Ay. Have you taken sociology?
No.
Okay. I'm gonna make you sit through a story now. Did you know that there was a story in Detroit about 35 years ago where there was an accident at rush hour? This woman was horribly injured, bleeding out, and nobody called the cops, and she died. And the next day, police came and asked people along the same rush hour, did you see this accident yesterday? If so, why didn't you call anybody? And to every one of them said the exact same thing. What did they say? Somebody else did it. That person died because they all thought somebody else would do it. Golly, people speak on it. All right. You're causing life here, people. All right. Scrap this, sorry. Let me work with what you have here. Submarine is 2 meters. There's a submarine. That's good. Submarine, bottom of the sub. The bottom of the sub rests 30 A cubic submarine. Oh, it's a cubic submarine, of course. That actually is much easier to deal with. Cubic submarine, edges 2 meters, 2 meters, edges 2 meters, submerged so that it's 30 meters down. All right, now are we all together? Okay, great. All right, so for the top, the force is still rho dA or PdA. I tend to remember PdA. But the weight density is still water, so it's still 9,800 newtons per cubic meter. The depth, what's the depth now? 30 meters. And what's the area? 4 square meters. Okay? That then, the total force being applied to that is something like 9,800 times 120. No wonder you weren't calculating that. What's 9,800 times 120? Get out a calculator, please. You'll need it all day. Something with 3 zeros on it, maybe more. Okay. 9,800 times 120. 1,176,000. And what are the units there? As far as the units, how do they work out? Newtons. That makes sense for force, yeah? Yeah. Okay. What about the bottom? The bottom has this bottom, and despite the fact that the force is being applied from the bottom, it still feels force from the bottom. So it's still going to feel that same type of situation. The weight density is the same. The depth will be different, though. Because this layer is at a little greater depth, then it feels a little more force. What's the force, or what's the depth now? 32. Now notice, although it's below surface level, we don't use a negative there. We're just going to use 32. That takes some getting used to, that going down is greater positives, but it is what it is. And the area is still 4 square meters. So 9,800 times 32 times 4 times 128. Was that? In newtons. 1,254,000? Thank you. Okay. All right. No, that's great. No, that's algebra based. That requires zero calculus. Right? What requires calculus is if instead of the top, which is always the same depth at every one of those square inches or square meters, it's the same depth, or the bottom, every one of these areas is the same depth, and therefore it doesn't require any calculus. But if you talk about the side, does this look like what you have? Okay. If you talk about how much force is on a vertical face, things are going to start to get a little more complicated. If you draw this here, actually, cubic vertical face, then this slice here, this slice has different depth, obviously, than this slice. And that has different depth than this slice. So, and this slice. Each slice requires its own calculation. A separate calculation. Then we need to add infinitely many slices. So what does that seem to indicate that we're going to be doing with calculus? What's differentiate or integrate? Integrate. We're going to sum infinitely many, infinitely thin slivers of submarine feeling force. Now, when you go to do this, force is still rho dA. Okay, what does the rho stand for? Weight density. The D stands for depth, and the A stands for area. All right. Now, you're going to want to first draw a picture and locate the axis. This is not usually something I worry about because I'm a math teacher, but in this case, you are going to have to define your axis. And you can do the problem in several ways, so it's crucial that you do communicate to the person. I typically try, on rectangles to make it first quadrant. And so I would draw the origin at the lower left corner. If I do that, then that whole system governs even all the way up to the surface of the water. I'm going to have to take that into account. All right. Now, each of these little slivers is a rhodie, so I really need to do an infinite sum of this. Let's go with the rho. The weight density does not vary with the depth. It's constant. And so that weight density can be pulled out from the depth. Now, that's a little bit of a stinker. The depth, is that to distance up from the axis to a slice or down from the surface to the slice? It's relative to the surface of the water. Now, where's the surface of the water? If my origin is at the bottom of the container, where's the surface of the water? What number? How far is it to the top of the cube? 2. And how far is it from the top of the cube to the surface? 30. So what's the surface at? 32. Okay, so the surface is at 32. All right. Now, based on just defining my axis, the measure from the axis up to a slice is y. So the depth is 32. Take away y, or 32 minus y. Right? Okay, that's depth. Check. Area. Now I'm talking area. I'm not talking the area of the whole cube. I'm talking each little sliver's area. So the area here, that's the area of each slice. Those are rectangles. What's the base of each rectangle? 2, constantly 2, right? That base for all rectangles is always 2. And what's the height of each? dy, yes, excellent. Infinitesimally small change vertically. So the height is dy, a super thin vertical slice. Delimits of integration now. The next option. What are delimits of integration? Take a guess. I heard somebody say it. 0 to 2, yeah. 0 to 2. Why not 0 to 32? Well, we're not summing up any force on the water of nothingness. We're summing up where's the force on the cube, and that's from 0 to 2. The cube goes from 0 to 2. You with me? All right. You crank that out, and we saw the units already, but this is newtons per cubic meter. The depth, what are the units on that? Meters. What's the depth on the 2, which corresponds to the width of the cube? Meters. And what's the dy? Meters. And so what are the units on our answer? Newtons. Okay, so whatever that is in newtons, that's our answer. And you can always use a calculator on these. To me, the star of the show is the setup. The integration is always going to be pretty easy, and so don't sweat. I mean, if you want to practice, you can. You with me? All right. Let's gradually then get a little tougher. All right. Say again we had a triangular trough, which this will be a pretty common problem. Physics books do and engineering books. So if I had this time, instead of the fluid is outside the object pushing in, now the fluid is inside the object pushing out. It is still, though, the same principle. The amount of force the fluid exerts trying to get out is still the sum of many rho dAs or PDAs, weight density times depth times area. Again, trying to get this in a first quadrant kind of case, I'm going to put my origin at the bottom left corner of the object. All right? So let's go through this. In this case, it's filled up with gasoline, which is not as dense. The weight density is 6,600. It's constant, so it can be moved out. The depth, I guess I need to fill in my picture a little bit. All right. A trough with a right triangular face, top edge is 9, side is 4, not on the scale, obviously, filled halfway up. this. I need to express this a little better. This is 2, and this is, okay? So as far as the fluid force, bless you, it's only in that lower section where what's been filled to, the 0 to 2 range, all right? So, let's go there. The limits of integration are from 0 to 4 or 0 to 2? 0 to 2. The gas is only in the lower 2 meters, so just there. The depth. So is the depth of a slice, D means, well, again, remember, we're adding, how much force does this little slice face, or force? Is it exerted on this little slice, and on this little slice, and on this little slice, and then we add them all. So when I go to say the depth of this slice, what is the depth? Is it relative to the top of the container? Or could it be 1 billion meters tall? It still wouldn't matter because the fluid level is at 2. And so is it 2 minus y or 4 minus y? 2 minus y. Now it's y because each slice has its own depth. You know, when this slice at 1 meter is drawn, then the depth is 1 meter. When this slice at 1.2 meters is drawn, then the depth is 0.8 meters. So it's always 2 minus whatever the slice is you're talking about. All right, area. The area, it feels like for area of each of these slices, you have to do a trapezoid. But that's actually, thankfully, not the case because as these get infinitesimally small, what happens to these 2 bases of the trapezoid? They start to approach each other, and it really is just really nothing more than a paper-thin rectangle. So you thankfully don't have to do some kind of crazy trapezoid for area of this. It's just the area of a rectangular slice. Because as they get infinitesimally small, the 2 bases approach each other and it's all good. So what about the area of that rectangular slice? The base. Is it constant like before in that cube or is it constantly changing? Changing. It's varying. What do we call a varying horizontal distance? We call it x. Right? Okay. So this distance is just x. The height, what is it? The height of this rectangle. It's dy. All right. Now that's great, but that's going to require a little bit of work here. Unfortunately, because we're integrating with respect to y, we must sub for x to get it all in x terms. Now, besides the relationship of the force going on, we also have this relationship that the x at any point relates back to the y at any point. In fact, the x is always on this line. So x relates to y through this line. What's the equation of that line? Oh, shucks. What's the equation of that line, people? Y equals 4/9 x. Yet one more reason to draw the origin there so we don't have to sweat the whiter side. Now, if y equals 4/9 x, then x equals 9/4 y. And so our substitution then would become something like 6,600, 0 to 2 of 2 minus y. And instead of x, we replace it with 9/4 y dy. That, in newtons, is our answer. So you can see then that a problem like this is a little harder because the base of each of those slices isn't constant like a cube. It's varying with that. It needs to be replaced with each y terms. Questions? Yes?
So why are your bounds 2, 0?
Because as far as where the fluid is, it was only, because it was only filled half the way up,
Oh, okay.
it was 0 to 2.
All
If it was all the way full, it'd be 0 to 4. Okay? All right. I didn't spend enough time going over the picture. Okay. Go to a symmetry case. Is this, am I Please make sure I want to make sure this looks like what you have. Okay. All right. Say you have a triangular case with symmetry, a trough with an isosceles face, top edge of 8 meters, sides of 5 meters is filled with water. Find the force the water exerts on the face. For now, I'm going to, again, force you to draw your origin at the bottom. Now, this isn't just going to be first quadrant, but we're going to use that symmetry as much as we can here. This here, top edge is 8 meters, so it goes what, from 4 to negative 4. Oops. Go away. No. Okay. All right. And then the height is, what did I say? This, oh, shoot. This is 5. This is 5. That's a bit of a problem because I don't have the height. That's a stinker. Okay. So I want the total force that's being exerted by the liquid trying to get out of this trough. Start with the basic idea. Force is the sum of many. Oh, good question. Yeah. Okay. So, I guess that made it soft on me. Do we agree with 3 by 3, 4, 5? The height is 3? Okay. Thank you. So, then the force is the sum of many calculations of force on each slice. Every slice has the same weight density. Pull it up. All right. What about the depth? What's the depth of each slice? Remember, I'm not talking the total. I'm summing up many calculations. The depth is 3 minus 5. This time they said it was filled with water, so I am going to on top of the container, so that's 3 minus 1. The area. Okay, I'm going to say this once in a while because it'll get people starting to drift, but this area is the area of slices, not the triangular face itself. Okay? So please don't give me base height divided by 2. That is not the idea. You're finding the area of a little tiny slice because each little slice has its own depth. All right, so when I say area, I mean the area of these rectangles. What's the base of each rectangle? Constant or varied? Varied. 1x or 2x? 2x. The height of each slice? dy. Limits of integration? 0 to 3. All right. Now, just in the previous problem, we have a mixture of variables which we need to deal with. So we need to sub for x. The shape of the figure. Use the shape. In this case, the edge is a linear edge. What's the relationship between y and x, between what the x is? Y is 3/4 x. So x is 4/3 y. We need to solve for x because we're going to make it all in y terms. So we could take that 2 out front, we could leave it in, whatever you prefer, but the x definitely needs to get sub 4 with 4/3 y. Hello. Integrate. And cha-cha-cha. What are the units on your answer? Newtons. All right. Thank you. All right. Let's go to slightly different now. Say you had a barrel full of water and it's laid on its side. So you're saying it looks like this. Okay? That's not great, but you get the idea. All right. Find the force applied to the circular face of the barrel. So how much force is pushing out against this circle here? Now, on circles, I beg you, in order to make your life easy, please put the origin at the center of the circle. The reason is when you go to write the equation for the circle, it's going to be much easier to write if it's at the center of the circle instead of shifted up. Okay, the circle equation gets gross if you put the origin anywhere else. All right, so I need to take the sum of all these little tiny slices, or each feeling force, and I need to aggregate all the force applied to all those little slices. The total force is the sum of many weight densities times depths of each slice times the area of each slice. What's the weight density here? That's water, so 9,800. Again, I'll give that to you if I forget, just ask me what's on a test. But again, you'll get it in your brain really quick. All right, the depth. What did I say? What's the radius? The radius is 0.5. 0.5. The height, by that height, I mean the height is 1 meter. Okay? Which means this goes to negative 0.5. All right. The depth. The surface of the water. Where's the surface of the fluid, or the very highest point of the fluid? 0.5. All right. So what's the depth of each slice? 0.5 minus whatever the y is at that point. That makes sense. If I did a slice here, it would be y is 0, and the depth would be 0.5. If I did a slice here, the depth would be 1 meter. So it seems to be working. All right. What about the area? The area, now that's, again, don't give me pi r squared, all right? I'm talking the area of each slice that's feeling force. What's the area of each slice? Constant base or varying base? 1 x's or 2 x's? 2 x's. And the height of each slice? dy. Okay, cool. Limits of integration from where to where? Negative 0.5 for the lowest y value to 0.5 for the highest y value. All right. Am I done, or do I have to do more? What do I have to do? Yeah, define x in terms of y. So 0.5 minus y stays, 2 stays. What is the relationship now between x and y? Any x and y here, they're related by virtue of being on the circle. What's the equation of the circle? Okay. Equals 0.5 squared. And so, what's x? Square root of 0.25 minus y squared. Now that integration is starting to get ugly. To do that without a calculator, now you're talking units, so everything's starting to get close. Okay? Still, you can do it with the calculator. Your answer would be with units. I assume you can put that in your calculator, so let's not spend the time. You with me? Questions so far? All right. Harder. I'm going to let you give this a go. It's a little too much me talking. You're just sitting there, it feels like. So, would you consider, just to make sure you understand the question, say that cylinder is the exact same problem. The radius is 0.5, the height is 1 meter, but this time it's laid on its circular end. What's the force applied to the side of the barrel? Total force applied to the vertical face. Try it on your own or with your math amigos. We'll go over it in a minute. This time, do put it in your calculator. Let's go all the way and get a numerical answer. All right. I have my answer. Do you have your answer? Not quite. Okay. Okay. ¿Listos? Any more stuff? Okay. Do you have something like 15,393.804? No? No? You gotta do this. How did you do this? Force is still the sum of many rho dAs. But this requires a little adaptation of thoughts. The weight density is still 9,800. The depth. How deep is, say, this slice here? When I have a slice here at y depth, or y level, the depth is 1 minus y. Got that part. Now let's talk the area. The area that is being felt actually is the area of that band right there. How do you find the area of that band? Yes, 2 pi r. If you unwrap it, if you were to cut that and unwrap it, it would be a rectangle where the total length of that rectangle is 2 pi r and the height is dy. What's the radius? Is it varying or constant? Constant. 2 pi, and the radius is always 0.5 times the height of dy. From 0 to 1, 0 to 0.5, what do we got? 0 to 1. The depth is, or the y values go from 0 to 1. Okay, that force, by the way, is not the same as if you lay it on its side. They are not equal to each other. Okay, last but not least, the trapezoidal trough. This is the one that tends to give the most problems, so I do want to get this in your notes. All right, so you have a gutter, which is clogged and filled with water. How much force is being applied to the trapezoidal end? The first base is 0.1 meters. The second base is 0.16 meters, or 16 centimeters, and the height is 0.08 meters. I would say let's go with origin there. All right. This is 0.05 if I take half of 0.1. What's the half of the top edge here? 0.08. Okay, and this is 0.08, obviously, again, not drawn to scale. Cool. All right, let's go here. the force is rho dA. I have a hard time believing you never know how to get started because you can always start there. What's the rho? If it's water, it's 900. Okay, the depth. It's filled, so the surface down to any slice, the depth is 0.08 minus y, eh? All right, the area. That's the area of these little slices. And again, don't fight the temptation to think, oh, I need the area of a trapezoid. They're at the infinitesimally small level. They're really thin rectangles, okay? So the rectangle's bases, constant or varying? Varying, gradually getting wider. 1x wide or 2x is wide? 2x is wide. And how high? 2y. All right. Now that's great. Everything's going swimmingly. What are the limits of integration? 0 to 0.08. Oh, that's cool. 0 to 0.08. 0.08 minus y. 2. Now let's replace the x. Ouch. This is ugly. So the x and the y are related by always being on that line. So we need the equation of that line. Now, if it doesn't go through the origin, it's strongly recommended you go slowly and do kind of a point slope approach. What's a point on that line? I can think of a couple different ones. 0.05 for the x and 0 for the y. Okay? What's the slope? Now be careful because it feels like 0.08 over 0.08, but really don't we need to go here? 0.08 for the rise, and the run is 0.03. 8/3, if you like. You see where we're coming from? So the equation of the line is just y equals 8/3 x minus 0.05. Therefore, x is what? 3xy plus 0.05. That then is one of the harder ones you're going to see is when you have to do this writing a linear equation because it's a trapezoid, it's not passing through the origin correctly. That's about as ugly as you'll see. I gotta be honest with you, in physics though, or in engineering, you'll have a much harder problem. Like instead of a vertical face, straight up vertical, it's more like an angular face at like a dam, for example. How much force is being applied to that dam? Well, then you've got a little more going on. But we'll build up. For now, that should get you going. All right. With that said, then you should be able to do 3, 4, and 5 on the homework set 74. Maybe we could get one of them knocked out. That's 3, 4, and 5 on the homework. Number 3, in case you don't have your book out, I'll put it up here, is you've got a rectangular face rather. The tank is 3 meters deep. It's filled. The weight density is 1,000. And what's the total force? Okay. In the interest of trying to get cut up here, I will put these for 70. What do we got here? 73, 4, 5. All right, I'll have these for 73, 4, and 5 up on my website. Use them as much as you possibly can so you can get down Okay, nothing's due today, but we will get caught up someday. Still not close to my record. Have a lovely day. No, you guys really don't ask that many questions. I have that record was supposed to keep it. They were asking me for their public name. So no, we won't get to it. You guys are way too smart. What group was that?